If you were in the market for a computer in early 1976, you were probably looking into the Altair 8800 or the MSI 8080 or this computer right here, the Southwest Technical Products 6800. Of these three, the 6800 gave you the most bang for the buck. One of its cost-saving measures was, as you can see, to eliminate the front panel of all the lights and switches and control circuitry that the MSI and the Altair had. It replaced the front panel with a monitor and ROM that provided the same basic front panel functions. But as you might guess, a ROM monitor could also do other things that the front panel couldn't. So it was actually a more powerful and flexible solution in the end, and it cost less money. So in the end, you found that subsequent computer manufacturers all went this route as well from this point on. The Altair and the MSI were one of the very few computers with a full front panel. Most everything from then on used a ROM monitor because it was a better and cheaper solution. Now, Southwest didn't develop their own ROM monitor. Instead, in order to save some development time and to reduce some risk, they used an existing monitor supplied by Motorola. It was called MicBug. Now, MicBug was truly a ROM. It was not a PROM. It was not an EPROM. So Southwest didn't have the luxury of tweaking it. They had to design their system to work with MicBug. And so that means using the address that was expected for the EPROM by MicBug. It means using the address for RAM that MicBug expected. I/O addresses had to match what was expected by MicBug, and even the I/O device for the console had to be the same. So some of the design decisions for the 6800 hardware were based on how the MicBug ROM monitor expected hardware to be. Now, during the first few years of this computer, that was no big deal at all. But later on, as floppy disks became the norm and disk operating systems and RAM became much more readily available, the holes that MicBug caused in the design of the 6800's memory space became a bit of a problem. And we'll address that in a later video. All right, so in this video, we're going to go ahead and do a quick demonstration of getting the computer up and using the ROM to take a look at memory and write a simple program. All right, the operator console we're going to use today is a ASR33 model Teletype. This would have been a very common solution as the operator's console on the day. It worked as your console, as the printer for your computer, and as the mass storage device for your computer with its paper tape reader and paper tape punch. Alright, so let's go ahead and get the computer turned on. Very simple, just a matter of hitting the power button. The noise you heard was the prompt coming up from the ROM monitor. Reset button we'll use occasionally whenever we need to go back into the ROM monitor from a program we might be running. Alright, let's take a look down here at the Teletype. I think I'll run it without the cover. It'll be a little bit noisier, but at least we can see a little better. Alright, I could use a new ribbon, it looks like. But anyway, the prompt is down here in the bottom corner. It is a dollar sign. That's actually the prompt for a slightly newer version of the ROM called SWTPC or SWTPC. Southwest eventually did develop their own monitor, and it's a slightly augmented version of MicBug. Most of what we're doing today will all be the same things. You would have done exactly the same way with MicBug. Alright, so you get a new computer. One of the first things you probably did was examine a few memory locations and maybe deposit some values to check out memory. So to do that, use the memory command, which is an M. Then type in the address. Let's take a look at address 0. And you can see it prints out the content of that, and it says that currently is FF. To do an examine next, you just type a dot and go on to the next location. And then you dot the subsequent location. So this would be the same thing as using the examine next on an Altair, for example. Now, one thing this can do that the Altair and the MSI couldn't would be essentially an examine previous. If you hit the caret, or which sort of looks like an up arrow, on the Teletype it literally is an up arrow. You can go backwards one location. So there's an examine previous function, basically. To change the location, you just simply type in a new 2-digit hex value. If I want to put in 0, if I wanted to put in 7F, so when you type in the 2 digits, it automatically writes it and verifies that it went in correctly. If there is an error, it doesn't write it for any reason, it'll actually spit back a question mark indicating an error. So that's another thing that the front panel system couldn't do when it did a deposit, is actually validate the data when it. When you're done, you just hit return and it automatically comes back to the prompt. Alright, so let's go ahead and put a program in. Back here in the early days with just 1K or 2K of RAM, you certainly didn't have an editor or assembler package. We didn't have a high-level language like BASIC running. If you wanted to write a program, you basically had to write a program in assembly language on a piece of paper, and assemble that in the machine language into the numbers that represent the program, and then key that in using a monitor like this or on the front panel in the case of an Altair. So I've written a simple program that prompts for a name, that you type in that name and then says hello back to you. And that's really all it does. And I'm going to go ahead and type in the bytes of that program now. I have the program starting at 0, so we'll put in memory command for 0. And now we just start typing all the values in. Whoa! I'm very crowded here with the keyboard and the camera. Alright, so CE 0027 E0 7E. Now the teletype is so slow that I have to wait for it before I type in the next number. If you're really good with the front panel switches, you're probably almost as fast as this. Now if you're on a normal CRT type monitor at 1200 baud or higher, then you can just type number, and it's a lot quicker of a process. So anyway, we'll keep going. This will take a little while. CE 00 36 BD E1 AC 81 0D 27 05 A7 00 08 20 F4 86 04 A7 00 CE Believe it or not, that's it. So that was a little bit faster than using the front panel for an experienced operator, probably less error prone as well. Alright, so those are the bytes of the program from 00 through 35. And to run that program, it's at 0. On a normal, or I say normal, on a front panel machine, you would examine address 0 and hit run. Here you say J for jump. With 4 zeros. That looks like it's running. It's asking for the name, my name. Type in Mike. It says hi Mike, and wants to do it again. So we'll type in Dave. And now it says Hi, Dave. Alright, so there we go. We got our program. It's up and running. Our teletype's getting noisier and noisier. So now the next step would be to save this so we don't have to type it in next time we want to demonstrate this to somebody. Alright, to get control back from my program, I'm going to hit the reset button. You can see I'm back to the prompt. And here is one place where the ROM monitor is a huge advantage over a machine like the Altair. On the Altair, there is no way to save this short of writing another program that punches the tape, entering that in the front panel somewhere else in memory that won't clobber this, and then punching the tape. And then you'd have to turn around and write another program to load it, and enter that in the front panel when you wanted to load it. One nice thing about the ROM monitor, it has a punch and a load command built in. So the first thing you have to do is tell it what range of data, what range of memory you want to punch. And that's up in the location A002, which is part of the monitor scratch pad. So we'll go up to A002. And they want the 2 bytes of the start address, which is 0000. And A04 is the 2 byte of the last 2 byte address of the last location to write, which was 0035. Alright, so this is all ready to punch. It knows the start and end address. Let's go ahead and take a look down here at the punch. Get it in view. And when I hit P, what you'll find is it turns on the punch for us and begins punching our program. So one thing you may find interesting here is that it printed out what it was punching, which is normal for the teletype, and you can see that it's all actually readable hex. It did not punch binary, it's punching SRecord, which is Motorola's version of Intel hex. The S1 is the start of it. Here's the address. S1 is the start, 13 hex bytes, starting at address 0, and here's a bunch of data. There's a checksum, and then you have another one. So it's all in essentially an ASCII hex format that includes the address of where each line goes and a checksum. So number one, you don't have to save and load contiguous space. You could have holes in it, and we'll see in a later video why that's important. And it has a checksum per line. So for error-prone loading systems like cassette or paper tape, it has a way to validate things are done correctly. The downside is, obviously it takes at least twice as much tape to load the same program. Even more because of the overhead of the SRecord, the address, and the checksum. Not a big problem for a little program like this, but if you start trying to load 4K basic or 8K basic, that double space overhead is a big problem. And eventually they got around that by having a small loader load with this SRecord format and then turn around and load the rest of the tape in binary. And we'll look at that in a future video too. Alright, now this tape is not actually done. Motorola requires an S9 record to signal the end of the tape. And the reason it didn't just write an S9 record is because you might now want to save another section of RAM if your program or data was broken up into 2 areas, all on one tape without it being done. But ours is all done at this point. So what I can do is I can go into local mode and type S9, which will put out. Well, I got a double S, but the good news is that will get picked up by the loader anyway. I'll just type it in again to be safe. Alright, now I'm going to turn the punch off. Actually, what I'll do is I'll go ahead and I'll write some trailer out here. Let's see. Alright. That gave me some null at the end of the tape. I've got a bit of a problem here. I've got old paper tape. I have a little tear there. Hopefully that won't be a big issue. So anyway, there is our program all punched onto paper tape. Alright, so let me put this back online. And we're back to our prompts. Alright, so now we can go ahead and try loading that program and see what happens. I'm going to turn off the computer so that it loses its content of memory. Turn it back on. And there we get our prompt. Alright, I'm going to go ahead and load this paper tape. Scrub I left over from the last time. Alright, and I'm just going to type the letter L, which is a load command. You'll see it automatically start the paper tape loading for me. This does not echo. It only reads it, does not echo to the paper. It's to save some paper. It saw the S9, and that's when it turned the paper tape reader off. It didn't even necessarily go all the way to the end of the tape. It saw the S9. You can see we're back to our $sign. So now if I jump to 0, there's our program. So my name is It Works. Alright, and that's it. We'll call that the end of this video. Nice to have that noise stop for a while. So as you can see, the ROM monitor not only gave you front panel functions, but the ability to punch and save without having to have separate programs. That would have been a huge thing back in the day as far as a time saver is concerned, because this is pretty much the only way to use the computer in the earliest days. So anyway, in the next video, we'll take a look at some more things. We might start using the cassette recorder and loading programs, and then eventually take a look at loading BASIC into this, and then eventually one of the disk systems in a later video.